Welcome back, everybody. This is the second part of the Grid Convergence Index method video. At the end of the last video, we executed the GCSI method or GCI method for the drag coefficient of the airfoil we were looking at, and this is the screen that we left out on. So this video, what I'm going to do is we'll go down through some of these numbers, what they mean, what we need to take out of them, and make a decision on what we need to do after. We'll also carry out this GCI not only for was not stop at the drag coefficient. We'll also look at pressure coefficient and lift coefficient. But as I said, I am not as hopeful that the GCSI method will be as plausible to take any sort of meaningful values from as drag will be. But yep, we'll see how they go. Why did I make that statement? It's just that I have done these a number of times, and lift also always acts well explicably, but in a manner that just makes it nonsensical. Anyway, we'll have a look here and we'll go over the reasons for that. So the GCSI analysis, I have a section here, and then I've summed everything up at the very bottom again in that function. The apparent order P, so that there again is a measure of the numerical behavior of the solver of this discretization space. Now in CFD and in numerical methods for that matter, there's basically three principal types of errors that you have. Number one is going to be a round off on your truncation errors, sometimes machine error, you can call it as that. And that there is the amount of figures or digits that the computer can store on, like, so for instance pi, Euler's number and other such numbers there that are irrational for that matter. How many digits can you store? Well, different computers and even different schemes, single precision, double precision, are going to carry different amounts of numbers. So they're obviously all incorrect. So there's an error there no matter before you even start, because we cannot capture every single number. So if we're losing numbers, we're losing accuracy. So yeah, we're always going to have that error. So we've tried to reduce that error as much as we can by using a certain computer that has a particular computer error. And as well, we've chosen in our solver to use double precision as opposed to single precision. Right? So double precision is carrying more digits, so 64 bits to play with there. So I believe it's an abscissa, and there's a couple of parts there in that floating point representation, or how the sign and the integer and the decimal places and the exponent is stored in 64 bits. That's written as a protocol effectively, i.e. double precision single point representation. Can't mind what it is, but we've chosen double precision, so we have done our best to reduce our truncation, our round off errors, or machine errors. That's one type of error which we have, but we're going to imagine it's negligible. The second type of error that we're going to have in here is going to be the error, our kind of iterative error, which is measured really by our residuals. We have stopped, and we've said that we have when we were running our solver, we chose 1e to the power minus 6 to stop iterating, to say that we've converged on a solution when the residual error was at 1e to the minus 6, or whenever, for maybe the residual. We also set that, I think, for the drag coefficient, maybe the pressure coefficient as well, and maybe the lift, I can't mind. But there are values in this that haven't reached that level of refinement, that are at 1e to the power minus 3 still. But what is that right though? If we iterated down to 1e to the power minus 10, surely we'd have a more accurate answer. Yeah, well, in principle we would, but we haven't. So there's an error there, right? But even if we went to 1e to the power minus 10, surely we'd go to 1e to the power minus 20. So we're always going to have an error here as well. So that's the second type of error, which is our iterative error, is what I call it, iterative error. So the first one I call the round off / truncation error. Second one, the iterative error. And the third one then is going to be our discretization error, or our numerical error. So we're dealing with, in real life, as far as we know, is a continuum. Um, Continuity, nice smooth differential equations, which our computers that I'm working on here cannot handle, and we need to break them down into small wee tiny lines so that we can model quadratically or linearly or whatnot, but it has to be polynomial based, right? So I have to bring it down to first order, second order polynomial. We're going with second order here. But yeah, that carries an error as well because it's going to be based on a Taylor series expansion. We've only gone up to three terms effectively, and then everything else has been a truncated. We've truncated the rest of the terms on it when we're going second order. So yeah, what about all them other terms? We haven't accounted for them, so we are off as well. We're still with an error. So the three types of errors are truncation / round off errors, our iterative errors, and then our discretization error. Right. So when we do the GCSI index method here for conversion, we are assuming that both our round off truncation error and our iterative errors are zero. They're negligible for all intents and purposes. We're satisfied that we've converged to an allowable and a permissible and a low enough value. 1e to the power minus 6, pretty good. And as well as that that we're running with a double precision format. We're storing as many digits as we possibly can with the hardware we have. And then the rest here then is up to our grid refinement, right? How best we can make this as much representative as a continuum as possible. So GCSI is measuring our third error, right? It's nothing to do with the other errors. So what is this apparent order? So the apparent order there is a measure of the behavior of this third error. This is high. Right? It shouldn't be more than 2 because our discretization is using a second order spatial. We're using second order spatial discretization on this, but we have higher values in here. Now the higher values in these could be numerical inflation on it. It could be that our grid is still very coarse. And what that's meaning there is that a lot of the variations that would otherwise be picked up aren't being picked up. We're smoothing over them. That's especially notable here now in the drag coefficient, which we wouldn't really expect to see much over 2. Now, it's not a lot over 2. That is good. I'm happy enough with that. If it was perfect, would probably be, and the best we could probably expect out of it would be maybe like a 1.8, 1.9, but we're over that. Pressure gradient is a good marker and is a good place to start with. Not pressure gradient, apologies, drag coefficient. I should be talking about drag coefficient here. Drag coefficient is a good place to start because, as I said, it is skin friction based. Its accuracy is going to be really as a function of the high gradients and around the wall. So our discretization is heavily biased towards the cells. So even though we don't have a lot of cells in this, most of them cells are where the cells need to be. So we should still be dealing, even with the core system meshes, with fairly good results here as far as the physics of the flow around the airfoil go. So this isn't a bad value. 2.251, not bad for pressure, or for drag, apparently. Now, the GCSI, which is the Grid Convergence Index, again here, we're dealing with a value of 0.37%, and then from a medium to fine, a 0.1728. And to be 100% honest with you, both of them are good. Once we're down below 5%, generally below 5%, if you're getting it awful tight to get this to make numerical sense, you could argue that, look, I'm below 5%. It's not bad. From 3 to 5%, you need to be at least in there, but it's not great. Between 1 to 3%, that's more solid. Right? You can rely more on the fact that your discretization suits the physics that you're modeling if you're between 1 and 3%, and you are marginally independent there. Marginally independent. So means there that the physics, the results I'm getting do not aren't going to change significantly with more mesh refinement. That this here, for the discretization scheme I'm using for this turbulence model, for this temporal model, that's good. That's as good as we're going to get. If the physics change, here, I can't rely on these values anymore. Right? I need to relook at them for new physics. And that's the danger again with getting too fine of mesh. You bring in new physics that were prior to bringing it in unresolved. Now they're in the radar. But at the minute, we're not too bad there between the coarse and the medium. I would not be happy with something over 0.3. In fact, I would not be happy with something over 0.1. At 0.1, we are significantly independent, I would put it as. And then so anything below 0.1 will be absolutely superb. We could say we're for all intents and purposes independent if you're below 0.1. 0.1 to 0.5, I'd say significantly independent. Okay, 0.5 to 1, highly independent, maybe. 1 to 3, adequately independent. And then maybe 3 to 5, marginally independent. Above 5, dependent. Okay, so let's go with that at the minute. So maybe there is an official guidance on that. I don't know. Leave it up to yourselves, but I'm going to be trying for something below 0.1, especially on a dry coefficient here. Right, so dry coefficient is probably going to be my best indicator of how well this mesh is bringing my discretization error down. Okay. So, and then the GCSI ratio. The GCSI ratio really is looking at the coarse mesh and the medium mesh, and then it's also comparing that to our refinement ratio raised to the power of our apparent order P. So there's another formula given by Roche in that, which gives a good indication of where we want. What we should be looking for here is a ratio that is equivalent to the value of our refinement raised to the power of P. I did say, yeah, that's what I did change that. Let me just double check. I think in the last video I did change that. I put plots, yeah, and that had a K in it for black. So let me just rerun this. It should come out blue, I think it's default. Yeah, there's blue. So I can see that a wee bit better now. I should have put that in as a best location. Obviously didn't to get it out of there. I'll check that. I'll do that one as well now the next time round. But yeah, what we're seeing here, the Richardson extrapolation results, this here, red star, this is the value that we would expect if we had, again, an infinite amount of cells or a infinitesimally small cell size. We would expect to land in at this value, our extrapolated result. So here we go, that's the limit. And we're moving nicely towards that. And we could say here that we're in an asymptotic range. And the asymptotic range, again, is going to be based off this GCSI ratio. It means there that we are converging, in other words, and converging in a healthy manner, that we're moving towards an extrapolated value. And in every subsequent refinement, the difference between the values is getting smaller. So we could see between, here's our coarse, medium, so we have a big drop there, but then find the medium is our next one with a smaller drop, and if we were to go again, we'd expect to see an even smaller drop. That's asymptotic. For the GCSI method to work, we must be asymptotic, which means we must be converging in. Now, we can be monotonic, which means that we're just going in a nice straight healthy line like that, or we can be oscillatory, which means that it's going up and down over kind of an average line. Either of the two will work. But the monotonic one is the most stable. All right, the other one there brings in numerical noise and so on, which we really don't want to deal with. The GCSI can break down for certain variables or parameters for that. By the way, how do we think about that variable parameter? I think it's safe enough to call it a parameter, especially in a steady state model, because it is a variable as far as we're doing it on the outside, because we're comparing things that can change. But as far as the solver is concerned, that is a characteristic of the flow for that discretized space at that flash point in time in a steady state analysis. So yeah, it has to be a parameter. It won't change as far as ANSYS is concerned. This is more or less saying the same thing, except what I'm doing, and where this one here was the extrapolation results, which was the value of phi, or in this case drag coefficient, against our characteristic cell size, or sorry, our characteristic cell size to the apparent order, where this one here is going to be our drag coefficient, our parameter of interest, against our characteristic cell size itself. As you can see, we can see the same general trend happening here. Okay, as a characteristic cell size there decreases. So just look, 5.5 down till 2.5. Some of these I've subscripted in reverse on the plots just to show change the direction slightly to show the different ways that they're running. And this one here is going to be again our parameter. And that there's measured up against the number of cells that we're dealing with. So as we can see here, as we went down, if everything was perfect, no cells at all, we will come down onto this extrapolated value, which is very similar to what we're looking at here. Results. So I just wrote these out. I just put these in as a structure where we can keep this in as a structure. And what it does mean is that I can use results in my function here, results, as opposed to having to put in a square bracket and write in each individual value. I can just use results. So P is 2.25. Again, wee bit high, but good for this level of mesh. If it was below 2, if it was at exactly 2, phenomenal. But we'll never get it at exact 2 unless we have some kind of numerical lies happening in here. But yeah, we're not that far off. That's not bad. The extrapolated value for phi is 0.0158, 0.059, 1588, 1.86. Yeah, I'm down pretty good, right? I'm down at least till a 10,000th. I'm equivalent, but I'm still a wee bit high compared to what the GCSI is calculating to be my true value. And how are we working with that one? Well, certainly within the GCSI of 2.1, right, I'm at 0.17, all right, 0.17. So I should actually just change them up. These are up here in 17%, don't forget, or 0.17%. This one here is the decimal equivalent of it. That's why it looks slightly different. So if anyone just is wondering, all right, that's the decimal form of 0.17%. Grand. Okay, so that is that one. So what would I do with this? Would I say that I'm independent? Well, I would say yes, I am significantly independent, but as I said, I would rather see that down under 0.1 if I can. So what will I do? Well, I'm going to refine my mesh one more time and see what it does here. Okay, what about the other parameters? Yeah, I'll look at them as well. But as I said, I wouldn't have the same level of confidence with them, especially with lift. Drag coefficient, or sorry, pressure coefficient, yeah, should be a wee bit better. But again, pressure is an integrated value. It's going to be so because it's an integral, it's kind of smoothed out. So it could be given false pretense in my apparent order P, that a false kind of sense of security that I have a nice smooth continuous function because it's calculated off an integral, which could be introducing a wee bit of a discrepancy there, but we'll be able to check that out. We will check that out, but first let's deal with this one. So I'm going to scoot myself back into ANSYS here, and I'm going to refine my mesh one more time. Right, so I'm going to take myself all the way back over to the left, and I'm going to put in more mesh cells or more divisions into this one. More cells, more divisions, smaller sizing. So where do I need to go with this one? Let's go take ourselves back into 5 here, right? And I'll go for finer. Right, it's going to be fine multiplied by R. Now, in MATLAB, you could automate this. We could run this here on a for loop. And what we will do is we're going to drop this course off. Medium goes to course, fine goes to medium. Fine, in fact, maybe that's just what I'll do. I could run a for loop independently, but now I could say here that medium is equal to course. Right, course is equal. fine is equal to medium. And then my next one here, fine is equal to medium by R. Have I wrote that the right way? I'm going to set my medium is equal to coarse by R. Apologies. My coarse is actually going to be what my medium mesh is. Right, that's it. My medium is equal to what my fine mesh is. Right, and then my fine mesh is going to be equal to, again, medium by R. Apologies for that. Right, and let's run them again and see where we're at. So our fine mesh here, we're going to bring ourselves into 220, 120, 120, and 180. 220, 180, 180. Was it 180, 180, 220? Going on in my head already. 220, 120, 120, and 180. 120, 120, 180. Right, head's going to get a wee track here. Head's starting to get melted. Right, let's just design this. So what I'm doing is I'm going to disregard this design point. I'm just writing in a brand new one here. Yeah, let's right click it. Don't click update all design points. It's going to do them all again. Let's just click on the row we want and update the selected design point. Okay, now what I'll do is I'm going to back on into MATLAB. Boof. And again, if I had this automated, what I would do is I would set all these different. But what I'll just do now is I'm going to take all these N2s, Control C, and I'm going to put them into the course, Control V. Take all these N1s, Control C, put them into the medium, Control V. And I'm going to change these postscripts to 3s. Change these postscripts to 2s. And I'm going to repopulate my 1s with my new results when they eventually come. So again, this can be automated. You can do it with a while loop if you're looking to keep going until your GCSI came down to under 0.1 or whatever you deem to be acceptable, and setting that, or maybe, well, your parent order, don't go on your parent order because you're most likely never going to hit an apparent order that's below the value that you know it should be at, where it should be below 2. And again, that apparent order for this discretized space is going to be parameter dependent, so it's going to be different for drag coefficient, what we're looking at now, compared to what we're going to look at next will be pressure coefficient. So as a matter of fact, what I should have did, let me just Control Z these here. I'm just going to keep my old space in there because I'm going to copy the whole lot of this, Control C, and I'm going to put this one into here like so, and this one execute 5 for, let's go for pressure coefficient in this one. All right, so I'm going to need, these will all have different values, but we can actually execute this now, can't we, because our other values should be the same. Apologies, I didn't Control Z enough of them. 2 and 2 and 2. All right, so I need to update them for pressure coefficient. And these ones here I'm going to just put back to the way I had them. So this was, I'll tell you what, I don't think I did enough Control Z. Sure I didn't. No, that's better there. Apologies. Just when I look at it, take these ones, Control C. And then my phi's come out of these because these are drag coefficients, not pressure coefficients. I'm going to look for pressure coefficient there. Right, there's that one. Yep. And then we will take these values here. These values here. change these to 3s again. Change these to 2s. These stay as 1. And then we need to calculate a new phi 1 for this one. These values here I do have in my table. And I may as well take them. So we're looking for pressure coefficient here. So I'm just going to keep this just for handiness. MATLAB untitled 2 pressure. So this is, as I said, for pressure coefficient, mesh lift coefficient, and drags, characteristics. Pressure coefficient is here. So I'm going to put in my cell sizes here, minus 0.305685. Wrong one. Oh, man, going all over the place. Minus 0. My second one here, 29988, and look, my third one. See the way this has jumped up again. So this here may be asymptotic, but it's not monotonic. It's at best oscillatory. So we should see a higher P here, 0.302916. All right, so there's all them values. So hopefully in my cutting and pasting, I haven't missed anything out. Oh, power and order, yes. It's actually P has gone down. No, we have the oscillatories and that. Well, why wouldn't we? I suppose we're still converging. What we have is a large delta between, we have a large delta from our first from our coarse to our medium, right? And then our second one here is a lot smaller, from our medium to our fine is smaller, and we are moving towards that value still. So yeah, why wouldn't we think that we're asymptotic? We're in an asymptotic range at least, albeit we're not monotonic. We're still oscillatory here. Okay, so yeah, and this is again something we would have expected, as within the drag what's happening, or the pressure coefficient. So pressure again is an integrated quality. We've probably started to move in somewhere where we're starting to bring in new physics onto this. All right, where it's starting now to see that separation bubble, where maybe it didn't see the separate. If there was a separation bubble, we're at zero angle of attack here again, but more than likely, there is wee little bits of separation there. Not because it's an NACA 0009, or not because we're at a zero angle of attack, but because we're at Reynolds number 50,000, which is transitionary. Anyway, at best, no matter what angle of attack we're at, it is a bogey Reynolds number, and it just so happens that's the Reynolds number where we are probably going to be peaking of velocity at in stem racing down a 20-meter track. We're going to hit that. So, you know, maybe it's a better case not to hit such a high speed. You know, keep it lower, keep it out of that sort of a drag and range and all. But no, that's get it down there as fast as you can. Get to the highest speed you can. Don't worry about it after. But yeah, 40,000, 50,000, 60,000, very hard to get a grip on there, right? We're not turbulent. We're moving out of laminar. Yeah, 500,000. Everyone says flow is turbulent on a plate. This is an airfoil. We're accelerating over certain sections of it. It's not a flat plate. It is an airfoil. So you can't compare apples and oranges that way. But that is a good apparent order. That's a nice apparent order there. Now, if I seen that for the drag coefficient, I'd say, you know, that's looking good. But pressure coefficient, yeah, dead on. I see other behavior in here. All right, let's see what we're at. Anyway, our and by the way, yeah, like you can just see where we're off. That was 1.4. We'd be doing pretty good. Grid Convergence Index from the coarse to the medium. Yeah, 2.6530. You know, it's thinking between here and here. Where are we? Yeah, we're still pretty good. We're adequately. I think it was adequate. I put. significantly. Can't mind, but between 1 and 3, as I said, between 1 and 3, we're in a certain range. We're adequately, maybe satisfactory, adequately independent, but not great. Here, I'm still between 1 and 3. I'm better, but still, we probably could do a wee bit better with this one here. That's what I'm thinking. I wouldn't expect to get this one down below 0.1, but certainly we might be able to get it down below 1. So for this one, I'd also be interested in looking at what the next grid convergence method or the next refinement level will bring with respect to the analysis. All right, so this is behaving just like I thought it would, where drag is going to be the most well behaved or the best modeled using this discretization scheme for this physics setup, which is a transitional flow modeled in a steady state setup or model, which we know we're going to run into difficulty straight away. Now this should be converged by now. Let's get a look. Yep. So we're finished here again. So now what we're going to do is we're going to enter in, let's go look at our drag coefficient first. Right? So our drag coefficient values are in column J. Right, let's just keep these together so you can identify. There's column J, drag coefficients, and we're back here on drag coefficient. So let's just confirm to make sure that we haven't messed anything up. So I should be, for my course, 0.0158877, 158877, grand, 158618, 158618, and then I'm happy enough that these are correct as well. So now for my new grids, let's check our number of elements. Has gone from 82,804 up till 165,600. So 165,600 elements in my grid. So again, do not think that these are evenly distributed. We have biases set up in the discretization, which means the vast majority of them are in around the airfoil, which means there that our drag is probably going to behave the best because it's pressure independent effectively. It's dominated by skin friction and by the resolution at the wall. Whereas the other ones aren't going to behave as well because they're also taking in, the pressure gradients as well. So and kind of the integral values. Now, what am I looking for here is my characteristic cell size, which is here, K1, which is 0.018. And by the way, just because I shifted everything up, what was medium to fine is now coarse to medium. It doesn't mean my medium to fine values here automatically move up to my coarse to medium. So it doesn't work like that. So I'm going to get new GCSIs for 3 to 2. They won't be the GCSI 2 to 1 that we had before. So make sure you do change all these. They do matter. Yeah, so characteristic cell size is 0018. Yeah, oh, sorry, as I was looking down at the 5s there and I saying, hey, that's bigger, that should be smaller. It is, because H2 is 2.6 there. 0018 9687. And then finally, my variable phi1 drag coefficient is here, is 0.0158524. So I'd be thinking that this is still asymptotic, still well behaved, because we could see that our difference, that was 158877, 1586, so it's dropped down by 2 ten thousandths, 100 thousandths, and here it's dropped down by 100 thousandths. So it's moved down even more. So there's our parent order. Yeah, has gone up more. We're still asymptotic as we thought. But now what's happening here, our parent order has gone up. And this is, again, something that would be expected with the pressure coefficients here, because this is, again, is dominated, again, by the skin friction. And you could see now what's going to happen as if we refine this anymore, we're going to start to get artificial values coming in here. Our P is going to automatically explode because of what's happening at the wall there. But no matter, look where my GCSI 2 to 1 is gone. I'm at 0.0422%. Right, so I'm down below point. I'm down below 0.5% on this, or is down below 0.1% on this. Apologies. I'm down below 0.1% on this. So yeah, and I'm a good bit below that. So I'd be thinking, yeah, look, GCSI the GCSI for the course, the medium mesh is good. The medium mesh is probably adequate. So if your computer was getting it tight to run the CFD for them amount of cells, and you were stuck with your medium grid, all right. So again, use the value of the fine grid of the iteration before this, as opposed to the medium on this. This is just tracking it. Yeah, you can. You'd be good. You'd be fine. You know, as far as relying on your data, you'd have a good margin. Because don't forget as well that the values in here have a 25%. Um, there's a factor of safety in these here, if you like, as well. So what we're looking at here is very conservative estimates. All right. So yeah, if you were getting it tight, or the computer was getting it tight to execute that many, to run the calculations out in increasing numbers of cells, you'd definitely be fine on the last fine mesh, which would be this one's medium. So 82,804 cells would be adequate for your calculation here, because the GCSI, given that it is asymptotic, the GCSI in it was low. Now it mightn't have been at the 1.163, can't mind. Maybe it did keep it, but yeah. But if your computer can resolve to that, yeah, certainly go down lower. P becomes less and less reliable. I could run this again. I might get a better GCSI, but my P could go crazy. And bearing in mind on that, so again, if we look at the formula here for calculating the GCSIs, where are we down here? GCSI eventually, right? This is R raised to the power of P. So as P is going to go up, take away -1, my denominator here gets big, which makes my GCSI automatically go down. Okay, so it's going to start getting artificial values here. So if P goes way out of whack, there's no point even looking at the GCSI, because these are being artificially inflated, right? Because P is going up, and if P goes up, it's exponential. Okay, so it gets less and less reliable. So we are still assuming that we have a good apparent order here. Right, so we start getting into the 3 range, we're getting out of whack. Right, we don't want to rely on that so much. So here we're just about okay. Right, so if it was me, what would I do? Well, if I was only really worried about the drag on this, which that is in STEM racing all I'm worried about, I'd be running with that, what is now the current fine mesh, because it is returning this level of accuracy, or this indicator here, which is very good. But the more I think about it, yeah, there is a good case there for running with this mesh here as well. It'll be faster. I can maybe test more airfoils, which is really what I want to do. And I now know the mesh that I want to run this physics at. I want to bring in not only the NAC 0009, I'll bring in the NASC 0012 0012. I'll even try, maybe a larger one. There is a 0006, but I don't think there's test data for that. But yeah, I now know what my grid will be, and I'm only concerned really with drag on this. Drag is the thing. I'm not looking to lift the car off the track, even though a slight lift would not be unwelcome, given that we're tethered to the track anyway. I definitely don't want downforce, so I don't want any sort of lift coefficients on this, or lift on it. And then the pressure, the pressure coefficient on it, like, it's good to know. That's what test results are given against. But definitely the drag is the biggest culprit for slowing my car down in this application. So drag is what I'm gonna stick with. But for me, I'm gonna go for this fine mesh. This is what I'm gonna use. I'm gonna run all my solvers now I'm going to run all my solvers, if I'm running steady state, that is, and if I'm running with my second order discretization schemes, and if I'm running at that Reynolds number, which I will be, I'll run it with this one here, 165,000. I'm not going to go any finer than that. I go more finer than that, P is going to go up. Yes, GCI might come down on that. Now my epsilon 2.1 might also come down, but it probably will not come down more relative to what's going on with P. So I could get, as I said, like an artificial sense of security out of that. Yeah, so as far as drag goes, I'm happy to run with that mesh. Now, another thing you could add in this is if you had an experimental value, you could see how far the extrapolated value that from the GCSI was off the actual value, which would give you an even greater metric and greater insight to your discretization. But we can eyeball it off a graph. I don't have the tabulated data for it, so I don't know what the exact value is, and I'm not going to put it in. Now, I could check Selig's work, the University of College of Chicago. I could check that, but I know he didn't check at 50,000. I think he was at 40,000 and 60,000 Reynolds number. But I think I know there's tabulated data for that, but not at 50,000. So yeah, if you want to go through all this again at Reynolds number 60,000, which is very easy for you to do from 2 videos ago, just change that in your design table, change your velocity to bring it up to 60,000 and run it again. Handy. Okay, let's just for the news of it, let's look at our pressure coefficient and see what this one does. So this was for let me see, GCSI ratio 1. Yeah, so these were for our first 3 grid points from our most coarse to our I'll tell you what I'm going to do. I'm going to snapshot them. And let's set them there until this OneNote project. Just so I can compare it, because I know these are going to be less predictable, as I said, because of our pressure, our integrals of the pressure and kind of the artificial smoothing of this. So let's try with our new values now. Right, so let me see, N22, 22, 82,000. So we're going to carry out the exact same exercise. Control X, I should have just, let me just Control C them instead of X in them. Control C, Control V, and then take my fine, Control C, Control V, take that up, change these postscripts from 2s to 3s. And these are now my mediums. 2, 2, and 2. And these are still 1s. Now, I can take these values obviously from here. They are the same. Number of mesh cells and my characteristic mesh size for my new and improved grid. And the only difference here is going to be what my value for drag coefficient was in my new fine. So only have one number to remember. And let's see, we scooter over here. Pressure, drag coefficient. Pressure coefficient is here. So this is, yeah, so this is scooted back up. This is, looks, it might even be asymptotic. It is, that's up by 3 thousandths, and then it seems to be by just over about 1 thousandths. So that there will be asymptotic. So that's 303,955. 955, is that what I said? Yep, 303,955. All right, so that's it. Everything else I am trusting was okay. Yeah, asymptotic range confirmed. Apparent order is up to 3094 as well. Yeah, 0.65. So we're down below our 1%. I'm just tell you what I'm going to do. I'm going to put these next to it because I want to do a comparison. And the best place to compare it if I have the numbers side by side. All right, so we have parent order 1.87, we've jumped up to 3.094. Right, so something not great is happening here. With that, we are asymptotic still, obviously, because we're moving towards a extrapolated value, and our differences between our epsilon there between the coarse and the fine, the coarse and the medium to the medium and the fine, is still showing a reduction. Which means there that we are asymptotic, but we are oscillatory by virtue of the fact that the numbers are they've moved to the other side. The GCSI ratio, yeah, has come up, has come down a wee bit, but our GCSI itself we've come down significantly there by using this mesh. So that's what I was saying. See, the GCSI 2 to 1 was 1.3736. And we made all our 2s the new 3s and all our 1s the new 2s. It doesn't mean that our GCSI 2.1 becomes our GCSI 3.2 in the new mesh here. So we could see that running there at the minute. So I'd still be using the fine mesh on this one. We are running at 0.2223 effectively on this one here, which is good. I don't think by further resolving it that this is going to drop down, much more. It might do it as P goes up, but we're now super convergent. We could see super convergence in these pressure based calculations, less so on drag, more so on lift, or not drag, pressure coefficient, sorry. So drag, we're going to keep away from pressure. So pressure coefficient and lift is pressure based as well. We can see superconvergence usually happening very early in lift as well. It usually converges awful fast. So not that they become less likely, but the difference, the epsilons there between 3.2 and 2.1, there's a massive jump on them very quick, and what it does, it introduces numerical misbehavior on it. So it doesn't happen. It doesn't happen without reason that these numbers go slightly askew. What we'll see happening more here, especially with the pressure coefficient, more so than the lift. The lift is going to behave awful bad. I know it will. I know my P's will probably be huge on it because of the speed of convergence. But with pressure, the pressure coefficient, what's happening here, I think, as we are resolving to a finer and finer mesh, as I said before, we're starting to pick up them transitions that weren't picked up on the coarser mesh. And when we start picking up them transitions there, we're changing the physics of it. We're changing the physics of this. So in GCSI 3.2, we were dealing with a set of physics which didn't, a flow which didn't have maybe separation bubbles or transitions in it. It was there, but we weren't resolved enough to see it. That's what was happening maybe at 3.2. With pressure coefficient and maybe so lift, slightly less because of lift, when we go down to 2.1, we are now seeing it. So we're dealing with a different flow regime as far as ANSYS or as far as the solver or this method's concerned. And we're going to start to get less and less reliable data. So again, we're looking to mainly focus on the drag coefficient for this application, if again we are resolved and sticking with the steady state view of what's going on. All right, so again, remember that with the pressure coefficient, likely as we resolve our meshes, we're dealing with a different flow as far as what's being solved in the CFD. We have things at a fine mesh in the flow that were not there in the coarse mesh, and so therefore we're not comparing apples with apples here. All right, what's happening in 3.2 and 2.1 as far as the pressure coefficient goes is different. You may as well be looking at flow over an apple versus flow over an orange, maybe. That's maybe a wee bit of a stretch, but that's as we approach the limit of comparison, that's where it's going to. With pressure drag, not so much, because as I said, we're less integral brace. We're dealing more with the skin friction, what's happening close to the wall there, as opposed to what's in at the flow field. Now, super convergent apparent order detected as well. All right, so that's something else that I've written in there as part of it. I have these two checks in here, and this one here is basically looking at how quick we're converging as well. And we'll see that coming up very, very fast in our in the lift force. So just to cap it off, at the minute I'm running with my latest grid. Right, I'm not gonna go any further because I see what the trend is. I've dropped to a GCSI for drag, which is the important one to me, below 0.1. Which is absolutely phenomenal. That means that my grid is ideal. It's absolutely independent for the physics that I'm modeling to capture drag. It's coming a wee bit unstable now with pressure, but still not bad. It's still very good with pressure, I must say. Still reliable enough, albeit my fluctuations that are probably coming in by the laminar separations and from the transition down at the wall are going to start to play havoc with this, which is saying, all right, you're at the limit of this mesh or at the limit of this turbulent model or at the limit of using this, looking at this in a steady state. Yes, refine more, but don't use a steady state because you know the physics are different. All right, I can't take my average values here at the medium and compare them to the average values at the fine and the average values at the coarse, because you know your airfoil is flowing in air in one case and it's in water in another case. It's not, but yeah, hopefully that point's driven home. If you want more explanation on it, give me a shout. Right, let's go then. Let's just do the last one. Let's just look at lift. Take all that there, Control C. What have I done? Control C, thank you. There we go. And this one here will be for lift coefficient. All right, so let's we'll look at these from the very start again. 165, 82, 45. So what I'm going to do is I'm going to shift these down the way, especially these two. Control C, Control V, Control C, Control V. 3, 2, 2, 2, 2, 2, oh, 2, and 2, 1, 1, and 1, and these values here, 41,000, these are obviously the old values. I'm just, because I'm going back to front this time, that's why it just looks crazy what I'm doing. But yeah, put the video back and have a look at it again. Right, so this is for lift coefficient. So let's look at all our values here for lift. On down, there we go. And here we are. So first I want to go back to what my original mesh was. So mesh elements in my first case was 22,032. My characteristic cell size H was 0.005 to 0025. And then while I am here, I may as well look at what my lift coefficient is. Drag lift. Right, which is, just put these in as a decimal just for clarity, 0.000454422. Right, that's a negative value. Is it? No. Right. So this is what we should be expecting, something very close to zero. We're at zero angle of attack, so we shouldn't really even concern ourselves with lift here. I know this is just going to go bananas in lift. I know what lift does at zero. We're just going to be playing with a millionth, you know, and a 10 millionth of a difference. It's going to be effectively zero. It should be at zero angle of attack. But again, at 50,000, we're going to have wee bubbles here that's going to drop pressure slightly over here where that same bubble didn't form on the bottom, which is going to lift it up a wee bit. And then in the next instance, it formed a wee bubble on the bottom, which didn't form on the top, and dropped it. Yeah, so we're going to have this going on here. But, you know, we may as well, for thoroughness, do all we can. 000120393. And then finally for phi 1 is minus 0.000114707. All right, so yeah. Let's see, everything else should be the same. Let's just make sure everything makes sense here. N3 is roughly doubling, which is good. H3 is, yeah, going down by a factor of 1.4. Yeah, so I think all that there should look okay. All right, let's run it, see what we got. All right, so look, we've converged nearly. That's what happens with lift. You get super convergence. So even in our very first one, we have super convergent apparent order detected. Unreal. Now you're going to always get that massive drop in it, and it's just shown in there by the graphs. Look at our apparent order, 9.73. So like that's absolutely out of the question. That's not going to happen. So that's it's nonsensical. In fact, in a lot of test results that you do, you're just going to cap that anything over 2, you're just going to cap. We're going to say 2 is our max theoretical value that we're going to get into this. If we go with things over, you can get away with going over 2, maybe up as far as 3, if you're using a second order system, that is, second order discretization. You can get away with it and you can rely, but after that, you're just going to be, seriously, your GCSIs are unreliable. But we said we're going to do this for thoroughness, and we're going to see. And there's no point in saying it unless we discuss it as well, unless we get down to the bottom of why this is happening. All right, so just take nothing at face value. All right, so this here is for let me just see. I don't have my the other videos. I was doing them at home and I had a splitter for my USBs. I don't have that here. I'm just going to plug this in just that I have. This here is let's see, is this coming on just for my writing pad? Right, there we are. Let's see, can I select that? I just write it in best I can. I don't want to delay much more. This is from lift down. And this one here was pressure. COF. And this one here was, say, how will we put this? It's not an iteration, so it is, I suppose. So let's say mesh refinement iteration 1, and this one is mesh refinement iteration 2. I should have just reported out the quantity of mesh cells as well. Yeah, actually, I can still use this here. Let's scoot that down. Right, and this here then is mesh refinement iteration 1, right, for lift. Okay, unplug this and go back to trusty mouse. All right, so let's update MATLAB with our new values. Actually, I'll just keep all the MATLAB here. So in the same way, I'm going to make my mediums, my courses, my fine, my medium, and then put in detail for my new, actually, this road here, medium first, Control C, Control V, fine, Control C, into my medium, Control V, and then all these here I'm going to update with my latest resolve values. Change the postscripts, 3, medium 2, and this stays as 1. All right, workbench, down, mount catch. There we are. Let's give myself a bit of space. So let's go for our mesh elements. So again, we were down to 165600. Characteristic cell size H1 is way over here at 0.00189687, and then our lift pressure lift is 0.123465928, and this is a negative number. Now, here we go. I reckon that P is going to be absolutely phenomenally large here. Just doing this because this actually is going to have absolutely no bearing on me changing or making a decision based on GCSI on lift coefficient at 50,000 Reynolds number on an NACA 0009 airfoil. Didn't go to a minus. Right, that's completely nonsensical. We have minus orders here. Yeah, so as you can see, this makes absolutely zero sense, which is to be expected in lift. So if nothing else, if a judge asks you and you are in a stem racing competition, well, did you consider how lift was affected? They say, well, oh yeah, we looked at lift, but at 0 degree angle of attack, if indeed that's what you're running with, lift wouldn't have been a considering factor. We'd take lift as negligible. And we'd also say at this Reynolds number that we're running at 50,000 on this airfoil, we are not going to be able to adequately predict lift using this model. Why didn't you use a different model? Well, again, because lift wasn't, a determinant factor in our decision to run with this airfoil. Drag was our main parameter of interest, and because drag behaves very well with this discretization scheme, as backed up by the Grid Convergence Index method for this this size of discretization, or this level of refinement, given that we have transitional effects at this Reynolds number, we are using 4 equations to try to capture them. Lift will not behave at lift and drag cannot be compared under the same physics at a particular grid refinement, at a particular level of grid. As a matter of fact, the lift, there's lift there, right? We could see here that even at the very roughest of grids, our extrapolated value, will be fine. We're down there at minus 12. Like that's roughly what, 12 to the power of 10 to the power 16. We're at 0. It's not going to work so well here. And in fact, this is validating that we're not asymptotic, so we cannot use the Grid Convergence Index method. We have to be asymptotic to use the Grid Convergence Index method. So it does not work for lift. Okay, you could argue with it that because again these fluctuations are very apparent at this grid resolution. Right, that's good for drag, bad for lift. And it brings up a very important point, and I'm going to finish off on this point. I know we're over an hour here, but this is hugely interesting stuff. And if you haven't gathered it, I love this stuff. The question is on CFD, like what are you modeling for? Are you modeling for good results, well-behaved numerical methods, or are you modeling to get the actual true physical reality? Well, you want both, but the true physical reality takes a certain type of discretization to expose and to adequately report on. Whenever we're making simplifications, for instance, using a steady state model, it'll only take us so far. And grid independence it only takes care of discretization error. And that discretization error is going to be a function of the physics of the flow field. If you change the physics of the flow field, which isn't being done by changing the mesh, but it's being brought to light by refined mesh, everything goes out the window. You can't have it both ways. Yeah, you say, what's important to me? If it's safety important, if it's absolutely critical that you capture the amount of drag that this car is going to experience, well, yeah, use a steady state modeler, right, at 50,000 and run with, you know, 165,600 cells. That's what you run with, because we have absolutely phenomenal numbers for drag. Even though our apparent order is slightly high, it's not bad. We have a grid convergence index down to 0.0422 of a percent, right? That's not even 4.22%, that's 0.04%. That's phenomenally good. Even though the P is slightly high, which might be given a slightly, unfounded sense of security with that GCI, we also have to remember there's a factor safety built into that GCSI. So this would say to me that if I'm going to use a steady state model, if I'm running at 50,000, a Reynolds number of 50,000, and if it is only drag that I care about, if I run my grid at 165,600 elements, again using the bias that I used, if you use different biases, a different independent study, I'm going to get good results. I'm in a good place. However, if it is lift that I'm worried about, right, what I would look at in this, I would say, well, are you independent from your grid? Well, I'd say no. I said, look, we're not even at the point of grid independence. This GCSI is so much more than telling you if you're grid independent. It even tells you if your discretization method itself is any good. And to me, looking at this for lift, this discretization method is stinking. It's absolutely useless. We'll have to do something else. Well, maybe not the discretization, the model. I should say that they need to take that with a caveat. The model is bad. First thing I would need to do is look at transient modeling on this and then carry out maybe the GCSI on a transient model, because at the minute it doesn't work. But because lift, I don't really care about lift in stem racing. I'm gonna say that GCSI is fine. I'm going to use GCSI in all my methods, because it behaves well for because the discretization method is shown by it to behave well for the parameter that I'm interested in, which is drag. So I would say goodbye to lift. Pressure coefficient is slightly better, but again, it's not skin friction dominated. I'm not that worried about the pressure acting around the airfoil. It's not going to give me a great level of confidence. The superconvergence aspect of it, yeah, it's not bad. But I do know that that what's happening, the physics that are starting to come to light at this more refined grid level, are going to start playing havoc with this, with the GCSI method. And it is not feasible for me to run that level of grid refinement for one parameter, such as drag coefficient, and run a separate one for pressure, because I don't care about pressure all that much. If I did, what would you do? Well, I'd probably change my method. I'd go transient. I'd try something in a transient method that would satisfy the two of them. All right. I could step this one back to the coarse mesh, or not the coarse, the medium mesh, and probably run with it, and that would be a nice happy balance between the two. But at least with the fine mesh, I get a better idea of drag, which is an important one to me. So that is the Grid Convergence Index method as laid out by PJ Roach. It's brilliant, and I'd use it all the time. Not simply because it does show me how independent I am, how independent my discretization is from my solutions, but it also gives me an idea on how good my chosen method to model the physics of the flow is. So in this case, for drag, yeah, it's fine. I'll probably stick with that. So I'm going to close up this video here after what is approaching on an hour and 10 minutes. So thank you very much for sticking with me. I hope my maybe over the top discussions and explanation of these will serve as some benefit, and some of it will stick. If there is any specific point about this, as I said, I love this stuff. Be sure to send me a comment, email me if you can get the email on YouTube, I don't know, or look me up, put a comment in, and yeah, I'll be more than happy to talk about different elements of this with you, and maybe learn something from you yourself, if you see it from a different angle than I do. So yeah, thanks very much for bearing with me, and that is now mesh independence complete. The wrap it up, I am going to be going from now on 165,600 elements, and I will continue on the next series because I want to compare the NACA 0009 to an NACA 0012 0012 airfoil to see how the drag compares between the two of them. Okay, thanks very much, and I hope to see you in the next video. Thank you.